Sergey is going to give the second talk on his integral system in three-dimensional space-time, an introduction. So please start.
Thank you very much. Good afternoon, everyone. Konbanwa. Well, where we stopped yesterday? Yesterday we stopped at classical integrable models in discrete space-time. And suddenly I realized that I forgot to introduce graphical notations to explain what we are doing and where our variables live. So please remember, we are currently consider cubic lattice. N is vector, which is n1, n2, n3, and that's element of the cube. Typical picture, just cubic lattice. I try to draw cubic lattice. It's not the whole cubic lattice, it's just an element of cubic lattice. Yes, 2 by 2, 2 by 2 fragment. And you see that the main geometric object in this cubic lattice is 3D vertex. So let me draw typical 3D vertex. Horizontal, another horizontal, and one vertical line. So let me introduce directions. Also, I'd like to remind you, we deal with variables a, alpha, beta, and they depend on the point on this lattice. Alpha, beta take values 1 to 3. And also somewhere on the top, we use notations, short notations. A1, 2, it's for shortness A3. And A2, 1, that's A3 star, sort of conjugated pair of variables. Everything, of course, depends on n. Well, what is n? Now go to our picture. N is coordinate of this 3D vertex. So that's n, its coordinates. Then question, where we have A1, A2, A3, A1 star, A2 star, A3 star, which depends on a point on cubic lattice. Not a problem. They belong to edges. So for instance, here we have A1, both of them, 1, 2 of n. So A1 of n belongs to ingoing vertex, ingoing edge of vertex n. Well, here A2, both of them, star without star of n, and in the bottom A3, star without star of n. For outgoing, A1, both star, double star of n plus E1, so here shift happened. So therefore, horizontal line from left to right corresponds to shift by E1. Then here we have A2, both of them of n plus E2. So therefore, E2 is direction from back to front. And what we have on the top, A3, both of them of n plus E3. So now we see that all our dynamical variables, A, they belong to the edges of cubic lattice, and situation is quite natural. Next, we mentioned auxiliary linear problem. What does it mean in this particular case, for this particular picture? So let me repeat three-dimensional vertex. I repeat it. So here we have A1, both of them of n. Here we have A2, both of them but shifted, n plus E2. And in the bottom we have A3, both of them of n. And now, in blue color, I will introduce auxiliary plane. Auxiliary plane is just a section of cubic lattice. So blue points, they simply correspond to edges. And we draw section by the auxiliary plane. So auxiliary variables psi, they belong to these blue dotted lines. So if I'm not mistaken, it's 1, that's 2, and that's 3. Am I right? Most probably, no, I'm wrong. So they are 1, 2, and then 3. Auxiliary variables, they belong to the blue dotted edges. Here we have psi 3, here we have psi 3 prime, here we have psi 1, here we have psi 1 prime, and so on. And according to ideas written on the top, auxiliary linear problem here can be solved in the form psi 1 prime, psi 2 prime, psi 3 prime. It's already a solution since we excluded psi variables from inside of this picture. So this is x outgoing 1, 2 of A1 of n, x1, 3 fills A2 of n plus E2, x2, 3 of A3 of n. Then times psi 1, psi 2, psi 3. So that's solution. Ready-to-use solution of auxiliary linear problem. And this fellow, that's exactly matrix, which is described or explained above. And I beg your pardon, sometimes I write down alpha, beta, gamma, and sometimes I write down 1, 2, 3. For me, there is no difference. Alpha, beta, gamma, 1, 2, 3. It's just matter of your taste, how to count. Well, now, same vertex of the three-dimensional lattice, absolutely the same. But now we can shift auxiliary plane. Auxiliary plane goes through this vertex. And we obtain following configuration like this. This one and this one. Outer pieces of auxiliary dotted blue lines, by the way, they are the same as before. Since auxiliary plane just goes through vertex, therefore here we have psi 3 prime, here we have psi2 prime the same as above. And in the bottom, psi1, psi2, psi3. Auxiliary variables inside this small blue triangle, they become different, of course. But when we exclude them, result of exclusion will be x23 comes first, y comes first, since here we see a3 of n plus e3. Therefore, argument is a3 of n plus n3, x 1, 3, a2 of n, and x 1, 2 of a1 of n plus e1 times the same left-hand side, right-hand side as before. So that's solution of auxiliary linear problems. And zero curvature representation now means that result of this must be the same. x1, 2 of a1, x1, 3 of a2, x2, 3 of a3 equals x2, 3 of a3 prime, x1, 3 of a2 prime, x1, 2 of a1 prime in general. Here I just write everything for shortness. For instance, this argument for shortness, that's this one. A2 is this one. A3 is this one. And for right-hand side, in a similar way, well, that's zero curvature representation. Before it was written, where it was written before, yes, it was written here in slightly different way, alpha, beta, gamma instead 1, 2, 3. And symbol A is omitted, but instead of symbol A, we have symbol of a point on a curve. So how we write down such relations, that's our own choice. Well, in any way, equations of motions in discrete space-time, written here, written before, they can be seen as a solution of zero curvature representation, but solution, truly speaking, not very good, since in this solution, not shifted fields and shifted fields, they are mixed in some way. Well, then, one more comment. Yesterday, we observed that equation, our zero curvature representation, it looks like local Yang-Baxter equation. And I remember a question yesterday. Some people call it local Yang-Baxter equation. Some people call it dynamical. Question, what is the difference between local and dynamical? Answer, there is no difference, it's the same. But Yang-Baxter equation. Yang-Baxter equation lives in such space. In general, in most simple case, it must be 8-dimensional space. Our equation, Korepanoff equation, look on the top. It lives in 3-dimensional space. Well, it's people say that it's Young-Baxter equation, but understood in a category of tensor sum of linear spaces rather than in the category of tensor product of linear spaces. But there is no difference. It's the same. And why it's the same? It will be next page. Why it's the same? So matrix X in general, A, B, C, D. And matrix X takes part in Korepanoff equation, which is local Korepanoff equation or dynamical, doesn't matter. For each Korepanoff equation, there is local Young-Baxter equation. Matrix L can be introduced. Now matrix L is a matrix in end of C squared times C squared. That's usual matrix 8 by 8 with matrix elements. So top element is 1, rest are zeros. Then we have A, B, C, D. And here we have E, where E is BC minus AD. That's tricky. E is not determinant. It's minus determinant of X. So if we have such correspondence between Korepanoff 2 by 2 matrix L and Young-Baxter type matrix, Korepanoff matrix X and Young-Baxter type matrix L, and also general notation A capital is a set of A, B, C, D. Then equation x1, 2 of A1, 1, 2, A1, I don't like it, alpha, beta, alpha, gamma of A2, x, beta, gamma of A3 equals x, beta, gamma of A3, but different entries, x, alpha gamma of A2 but different entries, and x alpha beta of A1 different entries. So entries A, B, C, D in the left and in the right, how they are related, it's subject of this equation. So this equation is absolutely equivalent to equation L alpha beta of A1, L alpha gamma of A2, L beta gamma of A3 equals L beta gamma of A3 prime, L alpha gamma of A2 prime, L alpha beta of A1 prime. Well, this phenomenon, I think, is called Fermianization. And you can verify just by hands, writing down set of such equations in one case, in another case. In what here you have 3 by 3 matrix, 3 by 3. But here matrix is so 16 by 16. But anyway, set of relations inside, it's the same. They're absolutely equivalent. Well, and then, so go back to our business. Well, so that's Karipanov equation or local Janne-Baxter equation. Doesn't matter. You can replace all x by L. And we remember that model we start with, we used fields A, alpha, beta, such that by red color, I don't like red color, A12 equals A3, A21 equals A3 star, and so on. But later, suddenly, I decided to use small letters. Why I decided to use small letters, I have no idea. Strange decision. So that's classical Karipanov equation, where A capital, its algebraic notation, stands for set of A star, and matrix X is same as we used in a previous talk. I will show you where we used such matrix before. Here, you can see red color. So that's matrix X of the same type. And what is advantage of such matrix X? Of course, it's that X is 1. It's not my favorite choice. I prefer to have that X equals -1, but so far for some reason, I don't know why, we obtained that X equals 1. So therefore, after Young-Baxterization, after Fermatization, coefficient E is just -1. Well, and then next step. We are not quite happy with this form of equation of motion. We don't like it. But what we like? We like the following. We would like to consider all parameters, all fields, all variables inside left-hand side of Karipanov equation here, consider them as independent. And use Karipanov equation as a zero curvature representation to express dependent variables as a function of independent. So that's what is written in this line. Primed A 1, 2, 3, A star 1, 2, 3 as a function of A and A star. I don't give here explicit formulas. I think they are just misleading, some rational combinations, but they exist. One can derive them in few seconds, especially if you have Maple or Mathematica. Well, and thus, after such expression, we can talk about a map, functional map, which maps left-hand side variables to the right-hand side. In which sense I define map? So R1, 2, 3 being applied to any function of A, independent A, which sit on the left-hand side, and R is applied to function. Result must be same function, but now it depends on primed variables. So that's definition of functional map. So it's not set theoretical map, it's functional, it's different. Be careful. And then next step, why what I did is convenient. In fact, what we did, we choose direction of time. After this, that's observation. If we impose Poisson brackets for the left-hand side independent variables, And look here, I wrote very simple Poisson brackets. Here I must put huge question mark. Perhaps I did mistake. What mistake I did? Perhaps Poisson brackets for this particular map must be AJ, comma, AK star. It's 1 minus AJ star, then delta function JK. And then as a result, you will have the same Poisson brackets for primed variables. And here, big question mark. I simply don't remember which Poisson bracket is correct for this particular case. Maybe both of them. I'm not sure. Well, that's a straightforward way for quantization, by the way. Quantum theories will be subject of next lecture. Today we're talking about classical model, but look, map R appears to be canonical map for Poisson. It preserves Poisson structure, Poisson form. And of course, it's half step to quantization, just to replace Poisson brackets to commutators or to some algebraic relations. I'll talk about this on Thursday. So remember, this particular result to be remembered. That's very good, very interesting, very nice. Then, please remember that in my first lecture, I mentioned that in the theory of three-wave equations, there are two different Poisson structures. So in fact, we have two different Hamiltonian models. And the main difference between them is that before we consider vector type auxiliary linear problem, but another linear problem is scalar type. So let me remind you how it looked like in in continuous space-time. So we had d alpha d beta minus b alpha beta d what d beta, I think, minus b beta alpha d alpha plus product b alpha beta b beta alpha being applied to scalar linear variable would be 0. That's form of linear problem. And zero equality representation, proper form of zero equality representation for this particular problem give you equations of motion. Well, now what we're doing, we do replacement derivative to be replaced by difference. And what else can be done here? Formally, 1 minus b alpha beta must be q alpha beta. I think like this. Rather simple change of variables. And then after expansion of brackets, canceling similar terms, simplifying everything, we end up with this scalar form of auxiliary linear problem. Of course, now we have to talk a little bit about geometric, where our variables live. Well, picture is the same as before. We deal with cubic lattice. As before, very good idea is to use Q12 equals Q3, and Q21 is Q3 star. And altogether it's just Q. Q3. So as before, Q variables, they live on edges. Q1 of n here, Q2 of n here, Q3 of n here. That's in edges. Outgoing edges Q1 of n plus E1, Q2 of n plus E2. Well, picture the same as before. And auxiliary plane, also in the same way as before. I will draw section of cubic lattice by auxiliary plane, like this. But now look at structure of auxiliary linear problem. So that's auxiliary plane, section of cubic lattice. Q1 sits here, Q2 sits here, Q3 sits here. Also, we can draw orientation. But now auxiliary variables phi, it's a scalar. It belongs to the faces of auxiliary lattice. For instance, here we have phi A, phi B, phi C, phi D. Stop, phi D is different. Phi D, A, B, C, D, E, F, G. That's one hand side of auxiliary linear problem. But as before, when we move or shift auxiliary plane to the top, to the top could be also in blue. Then, as before, we obtain geometry or combinatorics of the left-hand side of Yang-Baxter equation, but with completely different content. Q1 prime here, Q2 prime here, Q3 prime here. Outer variables, linear variables, must be the same as before. Phi B, phi G, phi C, phi E, phi D, phi F. Phi A disappear, but instead of phi A in the middle, what we have phi H. So one linear variable disappear and new one appear. Then we can write down set of relations that are highlighted in green. Very strange color. Let me change this color. I don't like it. It could be blue. So this color is better. Well, write down set of auxiliary linear problems. For instance, for the left-hand side, it will be what orientation we use, like this. Phi F minus, yes, minus Q1 phi B minus Q1 star phi A plus Q1 star phi G could be 0. That's first equation. Second one is phi A minus Q2 phi G minus Q2 star phi E plus Q2 star phi C. And third one is phi F minus Q3 phi A minus Q3 star phi D plus Q3 star phi E could be 0. So that set of linear relations for the left-hand side. Similarly, write down similar set for the right-hand side, but with Q1 prime, Q2 prime, Q3 prime. And then just look what is their consistency condition. So zero curvature is always consistency condition. Well, right. You can do it by hands or you can do it using Maple, Mathematica, whatever you prefer. It's not difficult to find consistency conditions and find explicitly how map from left-hand side to right-hand side looks like explicitly. And verify that for this map, if you impose brackets Q1 star equals Q1 star, like this. So that's plus of brackets explicitly corresponding to Weyl algebra. Then your map will be canonical map. It will preserve this bracket. JK, JJ, delta JK, QJ prime, QK star prime, QJ prime, QJ star prime, delta JK. So map again is canonical. Well, for me it looks like a miracle. You start with nothing and suddenly you obtain canonical maps. Surprise. Well, canonical maps. So therefore, in general, we can talk about evolution. Evolution of defined on three-dimensional lattice or integrable system defined on three-dimensional lattice. And final part of my today's talk is why all this is interesting, why all this is important, and how to find general solution of classical integrable models in 3D space-time of both of models obtained. Well, here on the top of the slide, we consider two types of auxiliary linear problems. First one, that's scalar. Second one is vector. We need to take cubic lattice. By the way, not necessarily cubic lattice, may be more complicated. And draw section of the whole cubic lattice by an auxiliary plane. Well, now examples. Examples will be here. Again, cubic lattice as before. You can see that we can define two sections. For instance, one possible section is a section by a plane which is parallel to any of other planes, to most planes in this lattice. As a result of this section, you will obtain square auxiliary lattice. There is another way to do it. If you choose section which intersects everything, that section that we considered before when we tried to obtain zero curvature representation. Result of such section of cubic lattice, it will be lattice. I'll try to draw it. So we use blue lines like this, like this, like this, like this, like this, like this. Well, also two-dimensional lattice, but with more, no, here it's something wrong. With more complicated structure. Well, traditionally, this lattice is called Kagome lattice. And I think you could know better than me what does it mean. Am I right? Я думаю, I think go is wrong, but K and me must be correct.
Yeah, more or less good.
Arigato gozaimasu. Well, there are many types of lattices. Most popular are just square lattice and Kagome lattice. By the way, evolution operator. Evolution means that we simply move auxiliary plane and meet every time 3D vertices. Well, it's evolution. While square lattice, usually what happened with the square lattice is called sequence of Backlund transformations. It's not evolution, to be precise. But in both cases. And let me demonstrate what's going on for scalar linear problem. It's more simple to put notations. So 2 by 2 auxiliary lattice. So let us start to put auxiliary variables. For instance, phi 0 here, phi 1 here, phi 2 here, okay, phi 3 here. And we'd like to impose periodical boundary conditions. Therefore, on the top, somebody wants to write down again phi 0, since we must have periodical boundary conditions. But since this is a linear problem, keyword is linear, then boundary condition is not necessarily periodical. It must be quasi-periodical. Therefore, linear variable may acquire extra multiplier lambda. Here we may have lambda phi 2. Then, horizontal direction from left to right. Somebody expects again just phi 0. But since we have linear problem, we can introduce quasi-period mu, extra multiplier, mu phi 1, and therefore on the top lambda mu phi 0. And what's important, let us count number of linear variables. 0, 1, 2, 3. 3 linear variables. And let us count number of vertices. Q11, Q12, Q21, Q22. Also just 4 vertices. It's Euler's theorem. On torus with periodical boundary conditions, number of vertices equals to the number of faces. Therefore, we can collect all set of linear relations in a matrix form. Phi 0, phi 1, phi 2, phi 3 times matrix of coefficients. For instance, first row in this matrix is phi 0, it's minus q11 star, then 1, then phi 2, it's q11, q11 star, then minus q11. So that's first row corresponding to q11. In a similar way, q12, q21, q22. And all other lines, they will include lambda and mu. And in general, set of all linear relations can be written in a form, some matrix, huge matrix, which size is size of your auxiliary plane. Matrix depends on lambda mu, that's comma. And entries of this matrix, they come from our field variables which live on given section of cubic lattice. Then times rather big, huge vector of all auxiliary variables that are involved. And then everything must be zero. So that's complete set of auxiliary linear problems. And what we are interested in is this matrix, the square matrix. And we can define its determinant. J of lambda mu defined as determinant of L of lambda mu. That's polynomial of lambda and mu. It's some lambda power A, mu power B with some coefficients. Coefficients are polynomials with respect to fields. So same is valid for both linear problems. Doesn't matter. Same situation. And of course, auxiliary linear problem can be solved if and only if this determinant is zero. Determinant of polynomial is zero is definition of algebraic curve. All this is written below. So collection of all linear equations are written in matrix form. And we define in classical word determinant, J of lambda mu. This determinant must be zero. And that's definition of what is called spectral curve. That's the most important main object for all classical integrable systems. Well, now we have to focus on what is this algebraic curve. Each algebraic curve is characterized by its genus. So genus, G algebraic curve. And for square lattice, genus is huge. If you take lattice 10 by 10, then genus is 81. That's huge genus. I have some experience in theta functions, and most complicated theta functions I try to compute by hands. It's genus 2. Here, genus is much bigger. Well, and in this decomposition of spectral determinant, coefficients J, alpha, beta, most of them, they are called moduli of the curve. And moreover, remember that in the past, we observe that all our maps corresponding to zero curvature representation, they preserve some Poisson brackets. So they are canonical maps. And in all this stuff, also you can verify by hands that modular of the curve, first of all, they are in involution with respect to Poisson brackets provided. And moreover, they are conserved integrals of motion when you consider Kagame lattice as the evolution lattice as an auxiliary lattice. So they are integrals of motion of the evolution. There is no explanation of this, just miracle. Well, then, next step. Since we have algebraic curve, we can switch on the whole machinery of algebraic geometry. It's very lengthy story. Here I simply mentioned few heroes. It's Riemann, Hurwitz, Fay, Mumford, and so on. So idea is the following. If we have algebraic curve J of lambda mu equals 0, then on this curve there is J holomorphic differentials and two types of cycles, A-B cycles on topological algebraic curve. You can normalize these cycles such that cycle loop integrals are normalized, then with respect to other cycles, you obtain coefficients, omega coefficients, and then Jacobian of this curve, Jac of gamma G, is just G-dimensional torus, and on this torus it's defined theta function of the n from z to power g exp minus I pi n omega n plus 2 pi I zn. So formula is like this. I'm not sure about pi. Some people extract pi, some people don't extract pi. Maybe I is wrong. So G-dimensional theta functions, and they are main heroes in all this business. If I'm not mistaken, there is no clear criterion which matrix of periods corresponds to algebraic curve and which is not. So here matrix of periods, which enters definition of theta function, is very specific. But what is known about this? There is a universal statement that classical evolution operator, classical evolution is always linearized on the Jacobian of the spectral curve. So Jacobian is this guy, and Z belongs to Jacobian. It's just a G-dimensional complex number, complex vector. By the way, in my notes, instead of omega, I use notation gamma for galomorphic differentials. And most important identity in the theory of theta function from algebraic curve is so-called Phi identity. So Phi identity is rather complicated identity written here. Theta functions, the theta functions mentioned before. Z and gamma, so Z is point on Jacobian, gamma is vector of holomorphic differentials. So that's a B-quadratic equation, B-quadratic identity. Coefficients E, they are called prime forms. So E of AB, they're called prime forms. And all capital letters A, B, C, D, yes, just A, B, C, D. They're just points on the curve. And what is advantage of Phi identity? Phi identity is nothing but most general solution of Hirota bilinear equation. So Hirota bilinear equation is written below. We simply need to identify prime forms with coefficients for Hirota equation and integrals between points with the shifts along three-dimensional lattice. So the relation is 1-to-1. But Hirota equation is some particular case of integrable system in 3D. More general integrable system is obtained in the approach that I described, just general position. Hirota equation is particular case. And I understand it's very hard to work directly with theta functions. As I told you, if genus 2, then more or less we can write some software. If genus is greater than 2, then no one computer can compute something, anything. And therefore, for verification of all formulas, there is what is called reduction of algebraic curve to the sphere with selected points. It means reduction from genus G curve to, well, from theta functions to solitons. So solitons can be seen as a rational limit of theta functions. And instead of genus before, we can talk about number of solitons. So for instance, if there are no solitons, it means genus 0, nothing, just flat something. One soliton corresponds to genus 1. Two solitons corresponds to genus 2, and so on. And on the top, you can see just set how solitonic solutions look like, how solitonic theta functions look like. For genus 0, 1, everything not a problem, but for genus 2, you see coefficients in front of F1, F2, this coefficient. Well, in the literature, solitons with such coefficients, they are called general KP hierarchy. KP stands for Kadamts of Petviashvili. A-type Kadamts of Petviashvili hierarchy. So let me write down A-type Kadamts of Kadam. Petviashvili hierarchy. Maybe I'm wrong with transliteration of their names. Maybe Kadamts FTS. Question mark, but I'm not sure. Well, what's written here? Let me try to understand what's written here. That's some particular case. So all solutions can be written in terms of theta functions or in terms of solid terms. And important ingredient is a triplet of tau functions for scalar auxiliary linear problem. For vector type, something similar. Well, summary. What's important? That's important to look at linear problem. And very important ingredient is the determinant, spectral curve. Spectral curve is of great importance. Well, I think I must stop right now. It's already 6:30 in my time and 4:30 in your time. Thank you very much. Questions?